Let me open up one thing real quick for me, that way I don't accidentally go off topic. All right, so implicit differentiation. So it is a process to calculate dy dx or y prime when y is not written explicitly in terms of x, aka it's not always a function, right? So we can take derivative things which aren't functions of a defined curve. So curve does not equal function. And so this process has two main steps. You differentiate both sides with respect to x. Remember, in chain rule must be applied to the variable y with respect to x, and then you algebraically solve for dy dx. Calculate slope of the tangent line at any point. You evaluate this at some point. Sometimes you're going to see the evaluation written this way, where it's a large line, where it's dy dx with a very long line with an AB here. I don't know if you guys will see that. You might see that later, but I don't know if you'll see it in this book. All right. So here, I want to kind of go over the circle for a second, because this is the classic way you start this. This is an implicit equation, aka a circle is not a function, right? And let me just draw the circle real quick. Here's a terrible circle, right? This is not a function, right? Because here, if I just wander through with a little, it fails the vertical line test quickly too, right? And so here we have a circle. So here, does the slope of the tangent line strictly depend on the value of x? And the answer here is no, right? Because here, if I take some value of x, say like, so x squared plus y squared, so let's just take 4, right? Well, 4, I have a tangent line that looks like this, and also have a tangent line that looks like this. So depending on which y I have two massively different tangent lines, right? So the slope here is going to differ by a negative sign. So does it depend solely on x? In this case, no, right? It depends on y as well. Okay. So with the outline process, we're going to use is to calculate dy dx. And so let me show you how this is done very, very slowly. So here, I'm going to take the derivative with respect to x to the entire function, or the entire curve or equation, I guess, right? All right, so let's do this very slowly. D dx, or so the derivative of x squared plus the derivative of d dx of y squared equals the derivative of d dx of 25. I guess I should have left myself a little bit more room for this. I'll be okay. I'll be okay. I'm just going to use some of this room here, and then we'll find the equation of the tangent line over on this side. Okay. So here, the derivative of x squared is just 2x with respect to x, right? However, the derivative of y squared, well, y is some function of x, right? Y is a function of x. I don't know what that function is quite yet, right? And so here, what you do in this case is, see, I can explain it as you do is you take the derivative with respect to y, which is 2y, and then you do chain rule, whatever, and then you take its derivative of respect. See if I can explain this correctly without getting anyone confused. If I explain this first step correctly, everything else falls into place. This is exactly what you do, but I want to do it in a way that doesn't. Here, if I had, let me give you a different example real quick. If I had sine of x cubed is equal to something, right? Oops, hi. Can I have my brush back? Not my. Stop that. So if I have f equal to sine of x cubed, and I took its derivative, so if I took d dx, right, I would take the derivative of sine and then the derivative of x cubed, right? Well, the same thing here, because f is a function of x, right? And so we're going to have to do this. But here, if I do the same thing with y is some function of x. I don't know what it is, but I'm going to take the derivative with respect to y, and then the derivative of whatever this, then I need to take the derivative of y, which is y prime. Do I know what y prime is? No, that's what I'm solving for. And so when you see this, and with y, since y is a function of x, you're going to just take the derivative with respect to y. So this ends up being d whatever dy, dy dx is what you do. And so whatever this is, in this case, it's y squared. Well, the derivative of y squared with respect to y is 2y. And then I just write dy dx, which is just y prime. Okay? In fact, let me leave this as dy dx. And then here, plus the 25 is 0. Then, if I use this to solve, for dy, I'll get, so I move over, so I get minus 2x divided by 2y equals dy dx. So I move this over, divide by the 2y, cancel out the 2, so I just get it to be minus x over y. Okay. Now, if I want to find the tangent curve at this point, so I have a point, so I already have my point. All I need is my slope. And to find the slope, well, all you have to do is plug it into this. Okay. Well, dy dx is minus my x, which is 3 over 4. And so here we'll just plug, so here I have a point, I have the slope, which is equal to m, and you just plug it into this formula. X minus x1. We found tangent lines before. So once we do that, we'll have y minus 4 equals minus 3/4 x minus 3. Okay. And then if you want, you can simplify it from there. But this is the equation of that. All right. So that being said, if implicit differentiation means differentiate everything. If it's according to your independent variable, you take the normal derivative. If it's according to your dependent variable, in this case y is a function of x, you need to take the derivative with respect to y, or whatever that variable is, right? So you're going to do d of your function dy times dy dx. Okay. And then here, the derivative with respect to a constant is nothing. And then you can find tangent line. Let's do another one. It'll make more sense if I show you the next one. So yeah, let's go ahead and use the next page. All right. So here we're going to use calculate this using implicit differentiation. So we're going to take d dx of this entire thing. So the x cubed plus 3y cubed equals 6xy. Right. Now when we do this, I get d dx of x cubed plus d dx of y cubed plus d dx of 6xy. Okay. In this case, the derivative of x cubed is 3x squared. The derivative of y, remember when we have a y here, we're going to take the derivative with respect to y, which is 3y squared, and then we're going to add a dy dx. Here, we're going to have to use product rule, because here I have an x and a y, right? So I'm going to call this my f, and this is my g. So here, if I hold f constant, I'll have 3x, 6x, and then I'm going to take my derivative of y, which is y prime, Plus, if I take the derivative of this, which is just 6, times y, which we won't take its derivative, which is just y. So here we've not. So this is done by product rule. Okay. So if you want to find the equation to the curve at this line, how do we do this? Well, we still need to simplify. So here, I need to take everything that doesn't have a dy. So everywhere I see dy dx, I guess I should have left this as, I need to keep the same one. This will be dy dx. Y prime dy dx is the same. So I'm going to move all the dy dx's on one side and everything else on the other side. You could just easily write dy dx or y prime very easily. I just need to, whatever notation you're using, it's nice to be consistent, right? So let me just move it all to one side. So here, oh, before I move on, let me make my life easier. There's a 3 everywhere, so let's cancel out a 3 and make this a 2 and make this a 2. Okay. Then I'm going to leave this on this side, so it'll be y squared. I'm going to go ahead and switch to y prime plus, or no, move this over, so it'll be minus 2x y prime. So this term right here equals, I'm going to move this over, so minus 3, or nope, got rid of the 3, so minus x squared plus 2y. So everything that has a y prime, put it on one side, everything else goes on the other. And then we solve for y prime. So here we just factor out y prime, so we have y squared minus 2x y prime is equal to minus x squared plus 2y. And then we solve for y. So we just divide it out, x squared plus 2y over y squared minus 2x. Okay. All right. And so here we solve for the derivative of respect to y according to x of this equation, which is no longer a function, but here we still done it. Okay. The big thing here is to use product rule right here. So use product rule. So here you'll take this to be your f, this to be your g. So it'll be f, g prime, or f, right? Or, I mean, sorry, f prime, g. And we have this right here. Okay. All right, so if we want to find the line to here's our point, all we need is the slope. And so m equals y prime. Here's at 3, 3. So all we're going to do is type in 3 squared minus plus 2 times 3 all over 3 squared minus 2 and 3. I guess I should use some besides 3. Everywhere you see an x, put this, everywhere you see an x, put this, everywhere you see a y. This evaluates to be minus 1. So here we have y minus 3 equals negative 1, x minus 3. And then you can simplify from there. Okay. Let me do the last one. How did the 3's cancel out? I have a 3 everywhere. And so I'm just multiplying everything by a third. So here's a 3, here's a 3. I turn the 6 into a 2. Here's 6 into 2, just to simplify our numbers. Okay. All right, so let me just do this one last one. And so here we're going to use chain rule to solve this mess. And if I have time, I'll kind of show you how to do one on the homework. But since I only have 2 minutes, I doubt it. So let's just do this real quick. So calculate this by this. So here we're going to use implicit differentiation. All right, so let's take the derivative. So we'll have dx of sine of x plus y equals y squared cos, d. If we're taking implicit differentiation, we need to do it to the entire thing. Y squared cosine x. So this is dx All right. All right, so here we have this. And so we're going to do this as sine of x plus y equals dx of y squared cosine of x. We might go like 2 minutes over. So let's do this side first. So let's just do this. We'll call this f, and we'll call this g. All right, so here, if I take f prime, it'll be 2y y prime cosine of x. And then if I do leave f the same and take the derivative with respect to this would give me sine of cosine becomes minus sign. There should be a minus sign right here. Boop. There we go. Minus sine of x. All right. And let's take the derivative here. So here sine turns into cosine. Cosine of x. And then we're going to take the derivative on the inside. Well, the derivative on the inside, it'd be this with respect to x is 1. This with respect to x is plus y prime. Okay? So everyone sees, so here, this is chain rule. So here we just sine turns into cosine when we leave what's on the inside the same. Then I take the derivative of what's on the inside. Well, d dx of x is 1. d dx of y is y prime. Okay. Then what do we do from here? We move everything that has y prime to one side and everything else to the other. So here I'll have cosine of x plus y times a y prime. And then I'll move this y prime over, minus 2y y prime cosine x. And then I'm going to move this over to the other side, so minus cosine of x plus y. And then the minus y squared sine of x. And then here you just factor out the y prime, so it'll be y prime cosine x plus y minus 2y cosine x. And then you just divide it out. So we have y prime is equal to minus cosine x plus y minus y squared sine of x. And then here I'll have cosine of x plus y minus 2y cosine x. Okay. All right. So that's how you do that. Sorry to go 2 minutes over. So implicit differentiation is when you take a derivative with respect. The only thing you really need to graph in this chapter is you take the derivative of each individual opponent. If you have x and y multiplied, if you have some sort of function x and y multiplied together, apply chain rule. When you take the derivative with respect to y of a function of y, go ahead and take the derivative of the function and then just tack on y prime. That's really all you need to do.